All right, we are live. Audio and video is up and running. Welcome back to Statics. We are rocking and rolling in here. We are in lecture 27. Today, what we're going to do is continue our discussion of centroids. And I'd argue if there's any one lecture I really want you to take away from centroids, it's this one, because this one is the one that I think is among the most practical. It's also one of the more seminal topics in statics as to how to compute the centroid of a composite shape. This is a very ripe problem for the FE exam. This is also what I would expect many of your professors in future classes will expect you to understand how to compute the centroid of a composite shape. Just a quick recap. These are the formulas that we had derived from the lecture last time. And we had basically two sets of formulas. We had how to compute the centroids of the center of gravity. And so this would be the centroids for the center of gravity. But then there's also the expressions for the centroid. And largely they're the same. The only difference is with the centroid, we're looking at it in area, whereas the center of gravity, we're looking at it in terms of weight. Now, what we're going to do today is continue the discussion on area, but we're going to get a bit more practical. I mean, the homework that you did last time was all about deriving formulas, and I think it's a healthy exercise to go through so that you respect where these values come from. Really what engineers are going to be spending a lot of their time with when it comes to centroids is they're going to be computing them using the properties of simple shapes. In other words, most of the problems that we deal with, while we may not deal with centroids of just rectangles, but a lot of times, or rectangles and triangles and circles and whatnot, but a lot of times, a lot of the shapes that we deal with are comprised of a lot of simple shapes. Like, for instance, we've got this weird, plate here, which, that plate might just seem like, oh, that's just a random shape. I've seen gusset plates in trusses that actually look like this. So this is a very real, type of shape. I take a look at this and I go, you know what, really all this is just a collection of a bunch of simple shapes. And so if I know the properties of each one of those simple shapes, like what is the property of a rectangle, what's the property of a triangle, what's the property of a circle, if I understand those, then I can determine the centroid of quite a number of very challenging shapes. And basically all we're going to be doing is just utilizing this weighted average that you see here. So the sum of a times x divided by the sum of a, the sum of a times y divided by the sum of a. And if you think you're going to find this is a pretty straightforward approach. One of the other things I wanted to show you, which is a nifty little tool. I'm guessing that most of you, when you took CE 102, did you use AutoCAD? I think most of the people in here should have been exposed to AutoCAD. Am I correct? I know we switched from MicroStation to AutoCAD. Okay, so check this out. So I'm going to stop the share here. I'm going to pull up AutoCAD because I just can't help it. I thought it'd be a nifty thing to show you. So if you go to this is AutoCAD. It should be sharing now. For the most part, I'll go ahead and tell that the command that I'm going to show you, I'm not sure if it translates to Inventor, but you'll probably there's probably something very similar. So here I have just an empty blank AutoCAD drawing, and so let's just draw some region. I'm really just making this up as I go. Okay, and let's close that region. Okay, and I just made this up, so there's nothing, don't take this with a grain of salt, or just drew some lines together. And let's say I wanted to determine the centroid of this. Well, AutoCAD gives you a very neat little tool. First thing you have to do is you have to create what's called a region. So you type REGION, just a region, and press enter. And what you have to do is highlight all of the objects that you want AutoCAD to compute properties for. So I'm going to highlight all of these. And when you press enter, it says one loop extracted and one region created. I don't know if you see that there on the bottom. So it recognized that as a region. And now in AutoCAD, that's one object. It's not a bunch of little lines. It's actually one object now. And then there's a command called massprop, M-A-S-S-P-R-O-P. It's short for mass properties. And if you press enter, it's asking for the region. So you have to create a region, and then you select, okay, what region do I want properties for? So I'll select this region and press enter. And you can look here. If you see here, it's already starting to spit out a property. So it told us the area, it told us the perimeter, and then this bounding box is basically like the X and Y box, the coordinates of the box that this shape fits in. And to be clear, it's referencing these, let me zoom out a little bit. So it's referencing all of these values from the X and Y coordinate system. So like the green axis and the red axis, that's the X and Y. So if I press enter one more time, and raise that back up, you can see now it's computed a lot more. You can see the location of the centroid. You can see what are called the moments of inertia. We haven't talked about that yet, but to give you a real quick explanation of that, if the first moment of inertia, or if the first moment of area is the integral of x dA and the integral of y dA, then the second moment of area is the integral of x squared and y squared, and that's the moment of inertia. I think I mentioned that during the last example. We also have some other properties, the radius of gyration about each axis and so on and so forth. We can also write those to a file if we're interested in. I'm going to hit no. So just wanted to throw out some other tools that are available. AutoCAD will do some of this stuff for you as well. Let me stop the share here and go back to the slides. Any questions on that? So here I'll put something in the chat real quick, just so it's logged. So region to create closed loop, mass prop to compute properties. There, that's in the chat, so you all see that there. In case for some reason it didn't show up on the, like if you're looking at this on your tablet or something and it's kind of tiny. Okay, any questions? All right, so like I said, in most practical scenarios, let me close this drawing. In most practical scenarios, we're dealing with the centroids of very simple shapes. But you're an engineer, you're not expected to memorize every single little formula. So a lot of times your textbook or various sources, either online or whatnot, will have what I'm calling a centroid reference. And so basically it's just a table of basic shapes and showing, okay, where is the location of the centroid of these shapes. So for instance, if you look here at the triangle, okay, look at this dimension here, h/3. That should be pretty familiar from the homework assignment. We did a triangle. We derived the properties of a triangle, and we got the area was bh/2, and we got that the centroid was essentially a third from the bigger end of triangles. And so that that's all this is. So for instance, if you have a region on your composite shape that's a semicircle, okay, so let's say you got a semicircle. Okay, well, the area is pretty easy. That's just pi_r²/2. The centroid about the x-axis, well, it's basically just right down the middle, so that's pretty easy. But for the y-axis, we need to know how far is it from the bottom to that centroid. What is that centroid right there? And you could derive it if you want, or you could just look it up, and it's 4r/3pi. A lot of those formulas have already been derived for you. In fact, this is so critical to engineers. If you have your textbook with you right now, open the textbook and you'll see, if you go to the back cover, inside the back cover are the centroids of common shapes and areas. They're all listed right here. If you have like a digital copy of the textbook, this is in chapter 5. I just copy and pasted this. Now this list isn't complete. There's more in your book. I just didn't copy everything onto the slide. It was kind of big, so I just copied the ones that I think are really, really critical. Also, when you take the FE exam, these are going to be in the reference manual as well. So these are like very minimal references to engineers. NCES. NCES stands for the National Council of Examiners for Engineers and Surveyors. It's a mouthful. They write the FE exam. And so hold on, let me stop. Is everybody in here aware of the FE exam? Maybe I should start from square one. Okay. Just to be clear and just to make sure everybody's on the same page, the FE exam is the first of 2 exams that you take in order to be licensed as a practicing engineer. I'm licensed as a professional engineer in West Virginia. I took my FE back in 2008. To give you an example, it's been a while. But when you take the FE exam, which is written by NCES, I think of them as like the college board who writes the SAT exams and whatnot. The FE, when you take the FE, you're allowed to use a very, prescriptive set of resources, approved calculator, pencil, paper that they provide, and a reference handbook. The reference handbook, anybody could download this for free right now. It's actually worth it that you download it and check it out, because there's a lot of really good formulas and expressions. It's a really good resource to have. I still have mine from when I took the exam like 12 years ago. And in that reference are these formulas. When I took it, it was a paper-based exam, so I actually have a physical book. You can download it as a PDF for free. Just go to the NCES website. Maybe I'll post that or something on MU Online to show you how to do that. I want to go through the process of using these sort of pre-canned, pre-derived formulas to compute the centroid of an area, because this is a very critical. If there's any one skill with centroids I really want you to come away with, it's what we do today. When you're computing the centroid of a shape, I want you to take, there's 2 items I want you to look out for. The first is about your signs, and the second is about symmetry. Let's actually handle the symmetry first. The symmetry is really easy, okay? So let's take, for instance, this shape. Okay, this is an angle. Okay, this is an L shape. This would be a really compact one, but this would be like an angle that you see in steel design, like an L-shaped piece of steel. If you look at the centroid of an L shape, it actually exists like right here. That's where the centroid is. The centroid's actually not on the shape, which, to be clear, the centroid doesn't have to actually lie on the shape. Like think of a donut. A donut, where would the centroid be? It'd be in the middle of the donut. It wouldn't actually be on the shape. So that's not a requirement. But what I do want you to pay attention to is this line right here. Actually, that color's a little light. Let me use a little bit of a darker. Let's use this. I want you to pay attention to this line right here. That shape is actually symmetric about that line, okay? So because it's symmetric about that line, you'll find that the centroid lies on that line. And so where that can come into effect, like if you're computing the centroid of something like this, you already know where it is from left to right. You know that it occurs on that vertical line that strikes through the middle. You just need to figure out how high up it is. So whenever you're computing the centroid, try and make it easier on yourself if you can. Now let's talk about what's arguably the one that needs a bit more attention, and that's your sign convention. So let's say you were trying to compute the centroid of this shape right here, okay? Whenever you're computing the centroid, the idea is to take this and to break it up into simple shapes, okay? Now, I'm going to take my keyboard off of this because I want to make sure that I'm doing this well. I propose that this shape is comprised of 3 different regions, okay? There's a semicircle right here. So there's a semicircle. There's a rectangle. Maybe I'll use my green for this. that green rectangle. But then there is a hole, right? There's this circular region right there. Okay, so there's three different simple shapes: a rectangle, a circle, and a semicircle. Okay, so when I'm computing the properties of this, I might set up a table, something like this. The big thing to watch out for is your sign convention. When you're dealing with holes, a hole is basically just a region with a negative area because you're taking that material out of the plate. So if you look at the areas, you've got a positive, but this is a negative. And it's a negative because you're taking that material out. As for the coordinates, you're basically going to be doing the sum of AX divided by the sum of A. What about these X terms? Well, why do we have a negative, positive, positive? Why is that the case? Well, the reason that's the case is because here's your coordinate system. There's your Y-axis, and there's your X-axis. That purple region lies on the negative side of the Y-axis. That centroid, this centroid distance right here, that's going to be negative. So make sure that when you're expressing your coordinates that you respect the coordinate system. This might seem like a lot that I'm throwing at you. Don't worry. We've got a pretty comprehensive example that we're going to do to express this. This isn't going to be all that challenging. In fact, let's talk about that example. So I want to compute the centroid of this shape that you see here. I really like this example because it has all of the nuances that we need in order to fully understand how to compute the centroid, but it's also kind of easy to wrap your head around. I'm trying to figure out, let's say the point is right here. Let's put the point right there. I'm trying to figure out, let's say that's the centroid. I'm trying to figure out where that point is on the X and Y coordinate system such that if I had that plate, let's say this is a steel plate, and I had a little pin, I could balance that shape on that pin right there at that point and it wouldn't tip over. That's the perfect balance point. So that's what we're trying to find when we're looking at a centroid. What I'm going to do is I'm going to split this up into 4 shapes, and I'll show you that here in a second. But I want to be clear, you could split this up into a number of different shapes. There's a number of different ways that you could split this up. And as long as you're taking care of ensuring that all your what I'm calling proper bookkeeping, so keeping track of all the areas, the sign conventions, so on and so forth, as long as you're able to do that, you'll still get the same answer as long as you're accounting for all the area and all the distances. And I'll sort of show you what I mean by that here in a little bit. But with that, let me go ahead and share and bring up the notebook, and let's actually start putting some numbers down with this problem. Actually, let me see something. Give me 1 second. My apologies. I want to try something. Okay, I think that might be a little better from a latency standpoint. Okay, so here's our shape, and first thing I need to do is I kind of need to develop a strategy for how I'm going to go about attacking this problem. And so what I mean by that is I'm going to split this up into a series of simple shapes. I propose that we're going to have 4 shapes that we need to deal with. Okay, so I'm going to put those over here. All right, so let me draw. Actually, let me do this. I'm gonna squinch this up a little bit. So what I'm going to do is I'm going to split this up into the following shapes. I'm going to have this, this, and this. Give me a sec here. You'll sort of see what I'm doing here. Okay. So here's my shapes. I'm going to have shape 1. We'll call shape 1 the semicircle. We'll call shape 2 the rectangle. call shape 3 the triangle. And so that'll sort of be all my positive area. I'm going to, maybe I'll shade all this in. But then I'm going to have another shape, which is going to be this hole right here. And so I've colored that in with a different color. And so that shape's going to have a negative area. And so think about this mentally. Like if I were to take shape 1, shape 2, and shape 3 and add them up, that would give that blue shaded region here. But then if I subtract shape 4, that's going to basically represent this full shape that you see right here. Okay. So does everybody kind of understand what's going on from a strategy standpoint? Let me make this big here. Okay. All right. Now, whenever you're doing centroid problems, the best thing to do is to set up a table, because this is a very tabular process, because you'll see how this approaches. Okay, so I'm going to draw myself a table. Okay, and first thing I'm going to do is I'm going to have a column over here. We're going to call it shape. Okay, and we're going to number them, but I'm also going to try and describe them a bit. So let me drop this down a bit. So 1, we're going to call this the semicircle. We're going to have 2. Shape 2 is the rectangle. Shape 3 is the triangle. And shape 4, I'm going to call the circular hole. Okay, and put that down like that. Okay, so I've got 4 shapes that comprise this region. Okay, there's no rules as to what order that you do this in, just as long as you apply your basic formulas appropriately. And your basic formulas are x bar is the sum of xa over the sum of a, and y bar is the sum of ya over the sum of a. This is basically what we're doing. And as long as we follow this, we're good to go. Okay, so I usually think it's easier to start with the areas. So let's start off with the areas. So we're going to write the areas, and now let's put the units. This is area, and this is going to be in millimeters squared, right? Because all the dimensions are in millimeters. So let's start off with the semicircle. Okay, so I'm talking about this region right here. Okay, now let's use a little bit of common sense here. So we have a circle. What is the radius of that circle? Somebody help me out, or that semicircle. What's the radius of this semicircle based on the dimensions that are given? 60 millimeters, exactly right. The radius is 60 millimeters. Now, if the radius is 60 millimeters, what is the area? Like, how do you compute the area of a semicircle if you know the radius? Well, let's do this. If you know the radius, what's the area of a circle? Area of a circle is pi r squared, so the area of a semicircle is going to be pi r squared divided by 2. Exactly. So pi r squared over 2. So pi 60 squared over 2, which is, let's see, pi times 60 squared, 1800 pi, which is 54.87. All right. Did anybody else get that? I want to make sure I'm doing my math right. All right. Good deal. let's keep going. The area of the rectangle. Let's just see if somebody can tell me what is the area of the rectangle. Because that's shape 2. And you could just tell me the number. You don't, I mean, you could do the formula if you want, but you can just tell me the number. $9,600, exactly right. And so I'll write the formula out. I'll call it like BH, which is 120 times 80, which is 9,600. And I'm not really worried about the units because I put here on the top that it's in millimeters squared. So I'm not labeling each of those terms. Okay, the triangle. What about the area of the triangle? Somebody help me out with that. What's the number? You could just tell me the numerical answer. 3,600. So yeah, 120 times 60 over 2. 3,600. Yes, that's $3,600. Exactly right. Now, the circular hole. Let's talk about the circular hole. First off, I want somebody to do the math and just tell me the answer. And maybe, I don't know, let's keep it simple. We'll say 2 decimal places. There we go. Now, Mr. Page, I'm glad you wrote it like that. Because if you look here in the chat, Mr. Page wrote negative 5026.55. Why is it negative? Because it's a hole. You take that area out. So this is negative pi r squared, negative pi 40 squared, negative 5026.55. Exactly right. He's exactly right. All right, let me use another color here real quick. So we've computed 4 areas. We've computed this number, this number, this number, and this number. Somebody help me out. I'm going to scroll this down a bit. I'm putting over here this Greek letter sigma because I'm going to be summing this up. I mean, go to your formulas up here. I need to do sum of XA divided by the sum of A, and then the sum of YA divided by the sum of A. So I need the sum of the areas. So let's sum up these areas right now, and let's see what we get. Somebody give me an answer here. We'll say 2 decimal places. Making sure everybody's awake this Monday afternoon. All right, 13,828.32. That's what I got. All right, so 13, 828.32. And maybe we'll go ahead and put the units there, square millimeters. And again, don't forget when you're doing this that the circular hole has a negative area. Okay. Now, all right, any questions so far? This should be pretty easy at this point. All right. Okay. Now, I find that it's easier to do one coordinate at a time. So let's go alphabetically, and let's start off with X. Okay. So let me explain what we're going to do here. Okay. So now we are trying to determine the location of the centroid, and the idea behind that is we're trying to locate the centroid of this really, weird shape. Well, I know the location of the centroid of each of the simple shapes. So let's take it one at a time. Shape number 1. Okay. Now, shape number 1, I propose that its centroid. Hold on. Let's put some symbols here. Its centroid is probably somewhere like right there. Shape number 2 is probably like right here. Shape number 3 is probably like right here. And shape number 4, well, it's actually where I put the little logo there. Maybe I'll delete that so that we can see what's going on. That's 4. Okay. So help me out. Okay, this is the X, this is the Y axis. X, Y. What I'm trying to figure out is the distance along the X axis. So let's take shape number 1. Shape number 1, basically I'm trying to figure out this dimension there. That's going to be X1. How far is it along the X axis to the point in question? So what is X1 going to be? How far is it along the X axis to the centroid of that shape? Shape 1. 60, exactly right. And so you could write that as 60. You could put R is 60, however you want to do that. The thing to keep in mind is that it's not always R, it's just R for this particular problem because of where that is, okay? So maybe I shouldn't do that. Maybe I won't do that. I'll just put 60. That's actually probably better. 60. Okay, the rectangle. How far is it along the x-axis to the centroid of the rectangle? It's also 60. Exactly right. The triangle. Now let's talk about this triangle. You all should be able to tell me this from your homework assignment. But if you have a triangle, how far is it from the big side to, maybe I'll put this up here. So this is B, this is H. What is that dimension? It's B over 3. You're exactly right. That's exactly right. And finally, shape number 4. How far is it from along the x-axis to that point? $60. There you go. See, this isn't so bad. All right. Now, what I'm now going to do is I'm going to, and like I said, I think it's easier to do this one coordinate at a time. So what I mean by that is, let's go off of our formula. The formula states that we take the sum of x times a, divide it by the sum of a. Well, I've already got the x's for each shape, and I've got the a's for each shape. And I've already summed up the a's, so now I need to compute xa. So we just take each one at a time. So what is 60 times 5654.87? So 60 times. So, and these numbers might get kind of big. That's okay. I'm going to round them to just the nearest whole number. I'm getting like 339,292. And so how am I doing that? I'm just taking 60 times that. 60 times 9,600, 576. I'm getting, let's see, 40 times. I'm getting 144. And then this is negative, so negative getting negative 301,593. Maybe I'll space that out a little better. Space that one out a little bit. And so again, I'm just, term by term, multiplying them up. All right. And if I sum those terms up, you know, that column of values up, I'm getting 757,699. Now I'm going to have somebody check me on that. So somebody tell me if they're getting the same answer I am. Wait. Let me see. Hold on. Let me see if I wrote these down correctly. 339,292,576,144,301. I'm getting the 699 as well. I got a couple seconds. I'm gonna go with that one. Check your digits because yeah, I didn't get the 300. Okay, all right. No worries, no worries. So here's the point. If I have the sum of x times a and the sum of a, then my x bar, which is the sum of xa divided by the sum of a, what is that? 757,699 millimeters cubed over 1328.32 millimeters squared. Look what happens to the units. Hold on. So that's millimeters squared. Look what happens to the units. Cubic millimeters divided by square millimeters. We got some cancellation, and I'm just going to be left with millimeters. So what do I got? 54.79. 54.79 millimeters, and that's what I got as well. So there you go. There's where the centroid is with respect along the x-axis. And so how do we finish this out? We keep doing the same thing about the y-axis. Okay. So now what we're going to do is we're going to have a similar column or similar set of columns. So now we need y terms. All right. So let's see if we can figure that out. So we're going to need y terms. I can do better than that. And we're going to need YA. So a similar multiplication. All right, so let's see if we can handle this. I'm actually going to do it in a little bit of a different order because I'm going to do it in order of difficulty. Okay, so follow along with me. Let's start off with shape number 4. Let's start off with the circle, the hole. How far is it along the y-axis to the center of that hole? So what I'm looking for is I'm looking for this distance here along the y-axis. We'll call that y4. 80. That's pretty easy, right? Okay, so let's do the easy ones first. So this is 80. Okay. All right. Now let's do shape number 3. Okay. So shape number 3, you know, maybe I'll just right here. I'm talking about this distance right there. So how far is that? All right. Now Mr. Page says 60, but Mr. Ashworth says 20. Okay. Remember, it's so what Mr. Page said, that's how tall it is. But remember that centroid here, you know, if that's a right triangle, we're looking for that distance right here. And that's h over 3, right? So that's going to be 20. Mr. Ashworth is exactly right. However, Mr. Ashworth missed something. It's not 20. It's minus 20 because we're going down on the y-axis, right? Because here's the coordinate system right there. And so we're talking about this centroid, we're going down. So this is minus 20. Does that make sense? All right. Rectangle. Somebody help me out with the rectangle. What's that one going to be? That's 40. There you go. Now, the tough one is the semicircle. Okay. So first off, let's do some chugging down here. I'm gonna cheat a little bit and go down here a bit. Okay. So when you have a semicircle, and that's the best semicircle I can draw, so bear with me. Let's say this is the centroid. Okay. You can express that dimension here as 4r over 3 pi. Okay. And I'm getting that directly from the the lecture here. If I go back to give me a second and you'll see what I'm doing here. I'm going to snip the formula from the slideshow into the notes. Okay, so here's the formula. And you can see where I'm getting that formula. I'm getting that right here. Okay, so that's just saying that, we're talking about this distance here. Here's our shape. And we're talking about, how far is it from the bottom to the centroid, and that's how that's expressed. Okay. Now, here's the problem, though. Okay, let's compute this for this. Compute 4r over 3 pi. So 4r over 3 pi. Yes, 3 pi, and r is what was r? R is 40 millimeters for this hole. Okay. So 4 times 40 over 3 pi, 4 times 40 over 3 pi is 16.98. Now, wait, oh, you're right. R is 60. You're right. I'm sorry. Yeah, hold on. Let me scroll up. Yeah, we're talking about the entire semicircle here. So yeah, R is 60. You're exactly right, David. My apologies. All right, so let me repeat this. 4 times 6 over 3 pi. So 25.46. Okay. So that's exactly right. 25.46. And again, thank you, David. Okay. So I propose that from the bottom of that semicircle to the centroid is 25.46. So that means I put 25.46 in here, right? Is that right? Add 80. Exactly right. That's the point I wanted to make. Okay. We're asking how far is it from the axis to the centroid. Okay. So really what I'm after is I'm after this distance. Okay. This is the y1 I'm after. And what I just computed at 25 was that distance. This is 25.46. So in order to get y1, I have to add 80 to that. So 25.46 plus 80, that's how I'm getting what is the real answer, 105.46. That's exactly right. And so here are my 4 values. Okay. Any questions on this? I know I had a little computational error there with the centroid, but other than that, everybody good? Now what you're going to do is you're going to do the same thing, only instead of the x times the a, you're going to do the y times the a. So it's going to be like that times that, that times that, that times that, that times that. You're going to multiply each of those associated terms just like you did before. I'm going to erase those circles. So I'm going to do that for you, or at least, you know, go with you. Somebody check my math to ensure that I'm not messing something up. Okay, so this one, I'm working from the bottom up. I got 402,124. And negative. Negative 72. And then this one, I'm tracking my decimals here. All right, 596, 389, 384,000, a negative 72,000 because that y distance was negative, and then negative 402, 124. I'm going to rewrite that so that negative is more prominent. Negative 402, 124. And so when I add that column of numbers up, I get 962, 265 cubic millimeters. Can somebody check my numbers just to make sure I'm not totally off the mark here? Is anybody else getting this same value here? I just want to check and make sure. $506,265. Okay, hold on. Am I negative now? Hold on. I think I forgot a term is what I forgot. Oh, I know what I did. I know what I did. Yeah, I know what I did. I had the I accidentally added the 384 twice. Yep, that's yeah. Yeah, so 506,265. Yep. Okay. I agree. Okay, so y bar is the sum of ya over the sum of a. And so now we end up doing the same thing. We get 506,265 cubic millimeters over the same area, 13828.32 square millimeters, which is, drum roll please, let's find that value here. I'm getting 36.61 millimeters. And so what are the coordinates of the centroid? 54.79, comma, 36.61. So that's X bar, that's Y bar. And so that would be the point at which if I printed this thing off using a 3D printer and balanced it off on the head of a pin, that is the point at which it would be balanced. Are there any questions about this? Any quick questions? Do you know what chart that page is on? That's a good question. Here, I'll turn through my book and see. All right. I'm getting it on page 238. But again, if you have the book, it's actually just in the back cover too. So look here, let me stop the share here. So here's the book, and if you actually just, here's the front, here's the back, and if you open the cover, it's actually like right in the cover. It's on, hold on. Yeah, it's on this page right there. That's the Centroid page. But I'm getting it on page 238. But to be clear, I have the one that's just the statics version. You might have the one that's the statics and the dynamics version, and it might be a different page. All right, I've got a couple practice problems for you to test out your understanding. This is some really critical stuff. Shouldn't be too difficult either. So hopefully you go through that pretty well. That's all I have, everybody. I will see you all on Wednesday. Stop the recording. Everybody stay safe, stay healthy. We'll see you then.